is Santosh, and here I am welcoming you to all. Today we are going to start our chemistry lectures from today onwards. So far we have also discussed English, and this side we are starting chemistry classes. In this, our focus is to qualify gate CSIR net, gate and CSIR net, CU set, Neet, TS set, or specific any other state exams. Now you see here, wherever we are going, this in some of the competitive exams, some concepts remains very simple and same. For example, if we take any chemistry topic from the GATE, the same topics are here in the NET, here in the Cucet, and here in the Neet. See here, when it comes to the Neet now, so it is little advanced. These exams are little advanced in nature. Okay, we are not going to cover this Neet completely, but some of the topics that are touched here. Now, as part of this, first we are starting organic chemistry. Organic chemistry. In this organic chemistry, first concept that we are starting is aromaticity. Generally, aromaticity comes in GOC. GOC nothing but general organic chemistry. And from this, in every exam, there must be one or two questions falling in this topic. Wherever you can open any previous year questions, from there you are looking one or two questions definitely from here. We are starting aromaticity. Aromaticity. So here you see, in aromaticity, what is meaning of aroma? Okay, meaning of aroma is pleasant smell, good smell. You can say pleasant smell or good smell. That is what aromaticity. Now we see, we'll go. There are compounds, organic compounds, inorganic compounds. Compounds are again divided into organic compounds and inorganic compounds. So we are completely starting here today organic compounds. This class is on organic compounds. So one of this topic is aromaticity. Okay, aromaticity. Now, so how to identify organic compounds that shows aromatic in nature, or they are in aromatic in nature? Now see, in olden days, most of the chemicals that are used to identify by the smell, but this is very dangerous, that we know. They may cause any carcinogenic diseases, that we know. But still we can go through some of the ways that we how to identify them in simple way. So here comes the Huckel rule. Here comes Haeckel rule. Haeckel's rule. Haeckel's rule. According to this rule, a compound, if it is aromatic, then it exhibits or it shows these are the characters. It should obey 4n plus 2 pi electrons rule. Okay, 4n plus 2 pi. It should be in planar in structure, planar in structure, planar in structure. It should be having sp2 hybridization, sp2 or sp hybridization. There should be a delocalization. There should be a delocalized organic pi electrons to be there. Now see what is, these are the characters we'll deeply discuss. Okay, 4n, here n is nothing but any integer. 4 is n is integer here, but most of the students, what they do in examination, simply they forget that, they think that n is number of cycles, number of cyclic structures in that. For example, they count, for example, this is naphthalene. This is what naphthalene is. Okay, they write that simply, these are two rings are there, that is why they write 2. But this is wrong. We should not do this. Okay, we should not do this. Okay, this is integer. Okay, planar is nothing but a compound should be in same plane. All the atoms should lie in same plane. For example, we can see ethene. Okay, we can say ethene, or for example you can also see benzene. This is benzene. All carbons are having sp2 hybridization. So you see here, if those who don't know what is hybridization, how to say quickly, how to identify quickly hybridization, let us see here what hybridization. For example, this is a carbon. This carbon is attached to how many other atoms? For example, this carbon is attached to this carbon, this carbon is attached to this carbon, this carbon is attached to this carbon, this. How many sigma bonds are there? Okay, if it is having 4, each sigma bond is connected to one more carbon. So 1, 2, 3, 4. Okay, now this is in sp3. Number of sigma bond minus 1 you add, and this is nothing but 1 is nothing but this is sp3. Now you see here, for example, you take this ethene. You take ethene. Now see here, this carbon is having how many sigma bonds? 1 sigma bond, 2, 3. So it is sp2. This is 1, 2, 3. sp2. This is sp2. Now you see, this is 1 sigma bond and 1 sigma bond. These are pi bonds. And one is sigma bond and 2 are pi bonds. Okay, so how many? 1 sigma bond and 1 sigma bond, 2 sigma bond. 2 sigma bond means sp hybridization. Okay, sp hybridization. Okay, now I hope that you are following this and you understood this, how to how to identify hybridization quickly. Okay, how to identify hybridization quickly. Now you see, we discussed this planar and 4n plus 5 electron rule and hybridization concept, and now come to the delocalization. Delocalization nothing but movement of electron above or below the plane of a compound or a molecule. You see here, above the below the nothing but, for example, you see electrons are always revolving. They are revolving inside the compound. Inside the compound. For example, benzene. So now see here, they always revolves. They always revolves. They are not in stable form. So we generally represent them as this, in this way. In this way, or you can write in this way also, or you can write in this way also. Okay, you can write in this way also. So this is, now you see, now a compound should be following these all. Okay, these are 4 characteristics. If it exhibits or it bears, then we can say it is following Huckel's rule, and okay, it following Huckel's rule, and then this compound can be aromatic. And if a compound, now see, if a compound having all these characteristics but not these 2 pi electron, okay, not 2 pi electron, it is following 4n electrons. It is having 4n electrons, 4n electrons, but not 2 pi electrons. It is in planar, it is exhibiting sp2, and it is also having delocalized electrons in it. These kind of, we say them anti aromatic compounds. They are anti-aromatic compounds. Now those compounds which do not follow aromatic rules or anti-aromatic rules are called non-aromatic compounds. They are non-aromatic compounds. What they are? Non-aromatic compounds. Non-aromatic compounds. We will be practicing so many examples now of these 3 types of compounds. Now hope that you are noting this. Pause your video for 1 second and then note this, or else you may be forgetting after some time. Now see, our first rule. Now we will go best example for the aromatic. First example for the aromatic compound is benzene. We take benzene. This is benzene. Okay, this is benzene. Now you see here, how many pi electrons are there? Each pi bond having 2 electrons. Each pi bond is having 2 electrons. 1, 2, okay, 3, 4, 5, 6. Okay, 6 pi electrons are there. Now you see, according to this, 6 pi electrons are there. Now you see, integers 4n plus 2 pi electrons. What is this? Is our first. This is in planar. Hybridized. The electrons also revolving. Okay, and each carbon is having sp2 hybridization. sp2 hybridization by carbon, 1 single bond, 1 single bond, 1 single bond, 3 single bonds, nothing but this. Okay, sp2 hybridization. Now you see, 4n plus 2 pi electrons. 4n plus 2 pi electrons. Now you see, n is how much? See here, n can be integer 0, 1, 2, 3, 4, 5, so many. Now you see here, but so many nothing, but here I am going to give you, for example, if we substitute 1 0 4 into 0 plus 2 pi electrons. Okay, how many pi electrons? 6 pi electrons. 6 pi electrons. Now let us substitute 1. 4 into 1 plus 2 pi electrons. Now you see here. 4 into 1, 4 plus 2 is equal to 6. 6 pi electrons. Sorry. 6 pi electrons. Now 4. 4 ones are 4. 2 pi electrons. 6 pi electrons. Now you see here. If we substitute 2, 4, 2 plus 2 pi electrons. How many we are getting? 2. 4 into 2, 8. 8 plus 2, 10. Now you see here. That either should have 2, 6, 10, 14, 18, 22, 24. Now these are deviations, or they are just slightly elusive, nothing but deviation. There is a something deviation. They are highly alluring. Okay, they are highly structured molecules, and they are unstable in their own. We'll be taking this one example and we'll be discussing that later, but they are here. There is a deviation. Now you see here. Now can you do this now? 2, 3. If we substitute n is equal to 3, then 14. N is equal to 4, then 18. Likewise. Okay. Likewise. Now you see. So here, how many pi electrons? Now number of n is equal to 0, but it is 6. Okay. N is equal to 0. Pi electrons. Now naphthalene. We take naphthalene. This is what is called naphthalene. This is what? Naphthalene. This is what? Naphthalene. This is benzene. This is benzene. This is naphthalene. How many pi electrons are there? What I told you, that each pi bond is having 2 electrons. So 1 pi bond, 2 pi bond, 3, 4, 5. 5 into 2 is 10. Okay, 5 into 2 is 10 pi electrons. 10 pi electrons, nothing but n is how much? N is 2. Nothing but see, 4n plus 2 pi electrons. Now n is, if we substitute n is 2, then 4 into 2 is 8 plus 2 is equal to 10. So it is satisfying Haeckel's rule. So it is aromatic in nature. This is aromatic. This is aromatic. Okay. Now this is aromatic. This is also aromatic. Now see, anthracene. We take anthracene. Now we will take anthracene. This is what? This is anthracene. This is anthracene. Now see, now count 1, 2, 3, 4, 5, 6, 7. 7 into 2, 14. 7 into 2, 14. 14 pi electrons are there. 14 pi electrons, nothing but what is the number of n? What is the integer? What is 4n plus 2 pi electrons? If I substitute n is equal to 3, then 4 into 3, 12. 12 plus 2 is equal to 14. Nothing but 14 electrons. Nothing but it is also aromatic compound. Anthracene is also aromatic compound. Nothing but if it is there, if you open the bottle cap, automatically some sort of smell that you are sensing. Okay, so that whenever you are doing research in the lab, this will very helpful. Okay, so this is anthracene. So this is the phenanthracene. You can say This is phenanthracene. Now we see here. This is what? Phenanthracene. Same like anthracene and phenanthracene. Okay. How many? 1, 2, 3, 4, 5, 6, 7. Same. It is also a aromatic compound. It is also aromatic compound. It is also aromatic compound. Now you see. What is this? This is planar sp2, planar sp2. Nothing but here one deficit of electron is there. Okay. Whenever is there any positive, see, remember this, whenever there is a positive or negative charge is there in any cyclo compound, then it is aromatic. Just imagine it is aromatic. Okay, it is aromatic. Now how? See, 2 pi electrons are there. 2 pi electrons. 2 pi electrons. 2 pi electrons plus 2 pi electrons. Okay, 2 pi electrons plus 2 pi electrons. 4n plus 2 pi electron. This is our rule, right? So 2 pi electron. So first integer is 0. So we are getting 4. This is aromatic. Now you see. This is aromatic or non-aromatic? How many electrons are there? 4 pi electrons are there. 4 pi electrons are there. Okay, 4 pi electrons are there. So are we getting any, in our integers have we seen that either we have seen 2 or 6 or 10 or 14, 18, 22, 24, but we haven't seen 4. So it is simply a non-aromatic compound. So it is not non-aromatic, it is anti-aromatic. It is following 4n plus rule. Okay, 4n plus rule only, not 2 pi electron rule. So this is. Now we will take one more example. Now cyclobute dianion. Cyclobute dianion. Now you see here. Now you see 1, 2, 3. Each negative charge is of 2 electrons. Just count, each negative charge is 2 electrons. Each negative charge is 2 electrons. This is 2 electrons, this is 2 electrons, these are 2 electrons. So total how many electrons are there? Pi electrons are there? Nothing but 6 electrons. 6 pi electrons. 6 pi nothing but our integer is 1. Okay, our integer is 1. So it is aromatic. Aromatic. So it is aromatic compound. Now see. Aromatic compound. Plus. Now we see here. Is this? It is aromatic. Aromatic. 2 pi electrons are there. So it is aromatic. Now you see. It is aromatic? No, it is not aromatic electron. It is not aromatic compound. No, it is anti-aromatic, because 1, 2 electrons and 2 electrons. 4 electrons are there. 4 electrons we haven't seen in our Haeckel's rule. It is deviation from Haeckel's rule. It is anti-aromatic. It is anti-aromatic. Now you see. Now you see. This. Now you see here. This is aromatic? No, it is not aromatic. It is anti-aromatic, because 4 is there. 4 electrons are there and each are there. So it is satisfying. It is satisfying the hybridization. It is in planar. There is a delocalized electrons are there, but it is following 4n electron rule, but not 4n plus 2 electron rule. So now we see. Now see this. Now this is 2 electron, 2, 6 electrons. So it is aromatic compound. So it is aromatic compound. Now we see. We'll write. Now we see here this. In this, these electrons are participating in delocalization. Okay, these are non-bonding electrons. You can say are lone pairs. You can say they are participating in electrons. I am using word here lone pairs and non-bonding electrons. We'll be seeing this concept in MOED mode, molecular orbital energy diagram. There we are seeing. Okay, there we are seeing. Okay, see here, aromatic compounds are highly stable. Okay, they are now come highly stability. I will explain you, but now you see here, highly stable. They are highly stable since in them always there is a delocalization of electrons. When there is a delocalization of electrons, there is a huge loss of energy. When there is a loss of energy, they are more unstable. They are stable in nature. Okay, they are also called diamagnetic compounds. Diamagnetic compounds nothing but when you are keeping this compounds in magnetic field, they slightly weakly repulse. Okay, there is a weak repulsion. Okay, weak repulsion forces are there in diamagnetic compound. Now all anti-aromatic compounds are whatever that we are identifying here, they all are paramagnetic. Okay, paramagnetic nothing but when we keep them in magnetic field, we get they shows or they exhibit the paramagnetism, nothing but they attracts each other. Okay, they attracts to the magnetic field, they attracts to the magnetic field, they attracts to the magnetic field. What they do, they attracts to the magnetic field. Okay, diatropic also we say them, diatropic molecules, compounds and paratropic compounds, both are the words to be we use them, diatropic, and these both molecules we are seeing them in stereochemistry also. Okay, stereochemistry there we are seeing, and in spectroscopy you most of the time you uses this whenever you take NMR spectroscopy of any compound, when you are doing any reactions in the lab. So there when you go for identification of compound, whether it is synthesized or not, so there you will be using this concepts. Okay, diamagnetic, paramagnetic, diatropic, paratropic. So we'll do some examples. Now see. Now before that, stability order of this aromatic, non-aromatic and anti-aromatic compounds. Let us see. Aromatic is greater than non-aromatic. Non-aromatic is greater than anti-aromatic. Anti-aromatic, nothing but they are highly stable, and comparatively anti-aromatic, non-aromatic are stable. Least stable are anti-aromatic compounds. Now we'll take example by the concept of electronegativity. Now En electronegativity, it will impact on shape of the molecule. Okay, shape of the molecule. So what is electronegativity? Say the force which is there in nucleus and that attracts towards it the electrons which are there in its orbital. Okay, for example, you see electronegativity. This is nucleus. These are orbitals. Okay, these are orbitals, or you can say shells, subshells. Now you see here nucleus, electron is there. Okay, electron is there, electrons are there. Okay, electrons are simply revolving there. So the distance, okay, the distance matters. Okay, the distance is matter. Electron 1, electron 2, electron 3. Now you see here electron 3 is very near to the nucleus. So nucleus, it holds it very tightly towards it, so it won't give it as simple as it is. Okay, now comparatively to the second electron, now the first electron, it can donate very, or it can give very simply because it is away from, and the force, okay, electrostatic, you can say nucleus force is very less to the electron 1 comparatively to the electron 3. This is what electronegativity. Now we see here how this electronegativity impacts here in aromatic compound. Aromatic compound. You see here now, pyridine. Now you see these are heterocyclic compounds. These are heterocyclic compound. Pyridine, nitrogen. This is what is pyridine. Okay, pyridine. Now you see these. Here we have discussed in pyrrole. This is what pyrrole. This is what pyrrole. This is thiophene. Yes. Okay. This is thiophene. This is yes thiophene. This is pyridine. Pyridine. Thiophene. Thiophene. Pyrrole. Pyrrole. Now you see in this. Now electronegativity you see. So here you see, since these are both nitrogen atoms, both are having what? Lone pairs of electrons. Okay, both are having lone pairs of electrons. All are sp2, all are in plane. Okay, sp2. But you see here it is involved in electronegativity. Sorry. It is involved in delocalization. These pi electrons are involved in delocalization. Okay, these are involved in delocalization. But in pyridine, these are not involved in delocalization. They are localized. They are what? Localized. Nothing but they are not participating anymore in the process of delocalization. Delocalization is nothing but movement of electrons in plane or out of the plane of a compound. So you see here sp2 all are. Now you see which is highly stable. So comparatively, now you see sulfur nitrogen. Electronegativity will increase when we go from the left side to the right side of the periodic table. Now you see nitrogen, it is highly electronegative. Okay, it is very highly electronegative and highly stable. And see here, this is highly stable. Nitrogen, it is having approximately 3 like nitrogen 5.6 something else. Tomorrow I will take you with number. Okay, electronegativity order. But this is the stability order. Okay, stability order. Now you see here, electronegativity En is if electronegativity is En is inversely proportional to the stability. Okay, electronegativity is directly inversely proportional to the stability. Nothing but if stability is high, okay, then electronegativity is low. If the electronegativity is high, then stability is low. Okay, this is what This is what? This is electronegativity. Now we take some more examples. Now tell me, I will be writing some of the compounds as your homework, and then you are categorizing them, which is whether they are aromatic or non-aromatic or anti-aromatic. You are also pointing that their hybridization. Okay, pi electrons how many? There in unique all the compounds. I will be giving this as your homework. Now you just do this. Now you just do these compounds for me. As your homework, and you have to categorize them. Now try this. Okay, try this your own and tell me. Okay, before you try this, and one more compound I am drawing here. Okay. 7. 1, 2, 3, 4, 5, 6, 7. This is also you try. Okay. This also you try. Trinyl. Okay. Trinyl compounds. Okay. Trinyl nothing but 1, 2, 3 trinyls. So hepta 7. Cyclo hepta trinyl cation. Cyclohepta trinyl cation. This is cyclohepta trinyl anion. You can write octa. Octa compounds. Okay, this is highly. Okay. One, two, three, 4, 5, 6, 7, 8. Perfect. Octa. Cyclo octa tetranyl. Okay, tetranyl annullines. Sorry, these are annullines. Okay, fine. These are annullines, but nyls compounds. This you try, but this is completely. You check whether it is satisfying hybridization. It is satisfying 4n rule or 4n plus pi electron rule. Okay. It is anti-aromatic or anti-aromatic, sorry, non-aromatic or aromatic. You try this. Okay, and it is paramagnetic or diamagnetic. You have to try. It is this. Okay, this you try, and some more I can give you, like okay, this is 10. You just write down. These are like 10. Okay, just imagine that is 10. Okay, but here I am giving one negative charge, two negative charges. Okay, 10 you just count. Okay, if is there any, no problem. See, why sir you are writing this? Okay, why you are writing in this, alternative? These are unsaturation. Okay, yeah, organic compounds are saturated and unsaturated. Saturated is nothing but when there is a double bond or triple bond is there in alternative places, and in where is there non-saturation, nothing but single hydrocarbons. Okay, simply hydrocarbons, alkanes we say them. They are alkanes. They are alkenes or alkynes. Paraffins or olefins. You can also say them. Okay, this is what you try these compounds. Okay, you try these compounds, and we'll be going little deep. Tomorrow we'll exercise some more examples on it, and then we'll be moving that the parameters. Okay, uh, parameters of like bond length. Okay, bond order. So and MOD also we are discussing, and then we'll slightly go into deeper the reactions. Okay, thank you very much.